Okay, we've talked a bit about Taylor series now, so let's see a few applications of Taylor series and some practical uses. Okay, so this will lead us into next week, where we're going to go back and see some applications and some actual procedural stuff and some hands-on concrete examples of where we're using these theorems and how to manipulate these things in a calc classroom. So let's start out with this problem. How many times do we expect to flip a coin before we see the first head? And we'll assume a fair coin to start with, but that doesn't necessarily have to be true. And we'll go back and do it when the coin isn't fair, right after we finish this first example of when it is fair. Okay, so we have to do some probability stuff, and if you recall that coin flips are independent, so the probability of flipping a heads is 1/2 each time, no matter how many times you do it. So the probability of flipping a tails and then a heads would be 1/2 times 1/2, or a tails, then a tails, then a tails, then a head is the product of those things, those individual probabilities. So the probability of one flip getting a head is 1/2. Probability of heads on second flip, but not the first, is, well, I need to go tails and then heads, and so the probability of getting a tails first and then a heads is 1/2 times 1/2, or 1/2 squared. Probability of a heads on the third flip, none before it, right? Each of these is the first time we see a heads, would be, I have to go tails, tails, and then heads, and so I have 1/2 squared for the tails, and then 1/2 for the heads, which would be 1/2 cubed, and so on. Probability of heads on nth flip, first heads, is going to be 1/2 to the n minus 1 tails times 1/2 for the heads, so it's going to be 1/2 to the nth. Okay, and so our expected value is going to be kind of the average of these things by how many flips they are. So our expected value is the average, the weighted average of these, of how many flips. Well, I'm going to have to take half the time it takes me one flip, plus 1/4 of the time it takes 2 flips, plus 1/8 of the time it takes 3 flips, plus ... right? Plus 1/2 to the n times n plus ... forever. So I can write this down as a series. I end up with the series n times 1/2 to the n from n equals 1 out to infinity. Okay, so how am I supposed to add that up? That doesn't look like a series that we know how to add up. It's not geometric. So I have to deal with that in out front somehow. If this n wasn't there, then this would be a geometric series and I could add that up no problem. So what do we do with this? Well, let's pretend that 1/2 is a variable. If I could rewrite this, that n out front kind of looks like I took a derivative because I get an exponent n and my variable, right? So if I could pull out that 1/2, this would look like n times 1/2 to the n minus 1, and that's still from n equals 1 to infinity. And now that looks like a derivative if that was my variable, if 1/2 was my variable. Okay, so let's do that. Let's make that a variable and then sort of evaluate at 1/2. Okay, so we're going to let f of x equal 1/2 times the sum from n equals 1 to infinity of n times x to the n minus 1. Alright, so there's our function. Then the expected value is equal to f at 1/2. Okay, so I just have to figure out what f at 1/2 is. Okay, but this looks like f of x is half of the sum from n equals 1 to infinity of the derivative of x to the n, right? Okay, but we have a theorem that says as long as I'm within my radius of convergence, and 1/2 is definitely in the radius of convergence. If I take the radius of convergence of this thing is -1 to 1. Or interval of convergence. Okay, so I can do this derivative trick, and we have a theorem that says that's the derivative of the sum from n equals 1 to infinity of x to the n. Right, the sum of the derivatives is this derivative of the sum. We can do that with this Taylor series. And now I do actually have a geometric series here. This is equal to 1/2, and that geometric series adds up to x over 1 minus x. And I need to take the derivative of that yet. But I can use a product rule on that, or a quotient rule. So this is 1/2 times, the derivative is low d high, so 1 minus x times 1 minus high d low, so x times -1 all over minus 1 over x, or 1 minus x squared there. So I've got 1 minus x plus x. This is 1/2 1 over 1 minus x squared. So f at 1/2 then is equal to 1/2 times 1 over 1 minus 1/2 squared is, well, if you do all that arithmetic, you get 2. Okay, so let's see, how does this change if my variable or my coin isn't fair? Well, it doesn't change much. So let's say the probability probability of heads is P, and tails is Q, with P equals 1 minus Q, right? I need the probability to add up to 1. Okay. And then heads on first flip. Say first heads on first flip has probability, well, I just need a heads equals P. First heads on second flip, it would go tails heads, and that would give me a probability of Q times P. First heads on third flip have to be tails, tails, heads, and that would give me a probability of Q squared P. First heads on nth flip, that would be tails n minus 1 times, and then a heads, which is going to give me Q to the n minus 1 times P. Okay, so the sum, or my expected value, is going to equal the sum of n times Q to the n minus 1 times P from n equals 1 out to infinity. Alright, and now this looks sort of more natural to use a power series. I can pull that P out front. So this is going to be P times the sum from n equals 1 to infinity. N Q to the n minus 1. Q is going to be kind of my variable here. And that looks a lot more like a derivative, just thinking of it as a power series. So let's rewrite it like it's a derivative. This is the sum from n equals 1 to infinity of the derivative with respect to Q of Q to the n. And so I get P times the derivative with respect to Q of the sum of Q to the n from 1 to infinity. And this is P times the derivative of, well, that's a geometric series again. Sum is Q over 1 minus Q. We had proven that the sum of the geometric series is 1 over 1 minus Q, but this actually starts at 1 and not 0, right? My index starts at 1, so the first term in the series is Q. The thing that goes on top is the first term. 1 minus the ratio goes in the denominator. And we get the same derivative this as last time. This is 1 over 1 minus Q squared, and P was 1 minus Q, so this is 1 minus Q over 1 minus Q squared. This is 1 over 1 minus Q, which is 1 over P. So the probability of heads is P. The expected number of flips to get the first heads would be 1 over P. So that's one application of Taylor series. We can sum up certain series that we might not otherwise be able to. Let's see another example. Of summing a series. So let's look at minus 1 to the n over n from n equals 1 to infinity. We had talked earlier, the alternating series test, I think, is when we saw this series, and we determined that this converges by the alternating series test, right? But we said we don't know how to calculate this yet. So what I'm going to do is I'm going to see if we can turn this into a Taylor series we recognize And maybe if you recall in the last video, I had some trouble coming up with a Taylor series for the natural log of 1 plus x. And what we decided after some math and some arithmetic was we decided that the Taylor series was actually -1 to the n plus 1 over n x to the n. And this series for the natural log of 1 plus x and the series that we have written down right here, they're really pretty similar, especially if I would evaluate at x is equal to 1. Okay, so let's see if we can do that. So if I pull off a -1 out front, I get the sum from n equals 1 to infinity of -1 to the n over n x to the n. If I would evaluate that at 1, that would be exactly the series that I wanted. So this thing is negative natural log of 1 plus 1 is equal to the sum from n equals 1 to infinity of -1 to the n over n. So that's equal to the negative natural log of 2, which is equal to the natural log of 1/2. So I can actually show, using Taylor series, that summation we could find to be natural log of 1/2. We didn't know how to add it up before. It wasn't geometric. It was sort of this weird harmonic thing that alternated in sign. But with Taylor series, we can actually evaluate it. Okay. So Taylor series are fairly useful in these computations, especially with probabilities and actuarial stuff, calculating those discrete probabilities or expected values, time till something happens. That stuff really relies heavily on Taylor series computations and being able to switch maybe from differentiation and summation, which order you do them in, or summation and integration, which order you do them in. A couple other things that we can do with series is let's say f of x is equal to the sum from n equals 0 to infinity of cn x to the n. Okay. So for example, I have e to the x is equal to x to the n over n factorial from n equals 0 to infinity. What if I wanted a Taylor series for e to the x squared? Do I have to go through and find all of the derivatives of e to the x squared? So this is e to the x squared is f of x, then e to the x squared times 2x is f prime at x. So at 0, that's going to be 0. How about we go to the next one? I get e to the x squared times 2x again, times 2x by the product rule, plus 2 times e to the x squared. That's f double prime at x. This is going to get kind of messy. And I can keep doing this, but taking these derivatives is going to be difficult to find the Taylor series that way. I know that if I'm trying to find it at 0, a lot of these things are going to cancel, but when I'm actually taking the derivatives, to get to the next derivative, I have to have all of this information so I can compute the next derivative. Well, that's not necessary, actually, because if f of x is equal to e to the x, then f of x squared is equal to e to the x squared, right? And if this is equal to the sum of x to the n over n factorial from 0 to infinity, this would be equal to the sum from 0 to infinity of x squared to the n over n factorial. So I can just substitute straight into the Taylor series and get a Taylor series for the other function. So I get e to the x squared is actually equal to the sum from n equals 0 to infinity of x to the 2n over n factorial. I didn't really have to go through all of the computations of finding out what are the derivatives of e to the x squared. I could use substitution. We can do similar things with multiplication by polynomials. So let's say I want to find x plus 1 times the cosine of 2x, and I want to figure out what the Taylor series is for this function. Equals this summation of some c sub n's, x to the n, we'll center it at 0, and I want to go from n equals 0 to infinity. What are these c sub n's? What is this? Well, I can start with the summation for the cosine, and if you'll recall, I had a negative 1 to the n, I have a x to the 2n, and I have a 2n factorial from n equals 0 to infinity. That's the cosine of x. So what I have to do is I have to put a 2x into the cosine function. So that's the first thing. I get cosine of 2x is equal to this summation from n equals 0 to infinity of, well, if I put 2x in there, I'm going to get x to the 2n still, but I'll have a 2 to the 2n as well. So it's going to give me a 4 to the n. And I'm going to include that with that negative 1. So it's going to be a negative 4 to the n. And the 2n factorial still stays down here on the bottom. The cosine of 2x is going to look like that then. Now I have to multiply by x plus 1. So let's multiply by x plus 1. Let's multiply by x first, and then add that to the cosine of 2x. So I've got x times the cosine of 2x is equal to the sum from n equals 0 to infinity of, well, negative 4 to the n, x to the, I've got an extra factor of x, so I'm going to get x to the 2n plus 1 from that extra factor of x. And I've got 2n factorial still. Okay, and now if I wanted to add these two things together, this would be x plus 1 times the cosine of 2x, right? So I have to add like terms. This guy only has odd terms. This guy only has even terms. So what we can do is I can integrate them and sort of write it out like this. I've got, well, the first even term is going to come from the top one. So when n equals 0 there, I get a 1. And then when n equals 1, I'll have when n equals 0 on the bottom one, I'll have a an x, and then when n equals 1 in the top, I have a minus 4 over 2 factorial x squared, and I get the same coefficient in the bottom, so plus a negative 4 over 2 factorial x cubed, and then a plus 16 over 4 factorial x to the 4th, and a 16 over 4 factorial x to the 5th, and then a minus 64 over 6 factorial x to the 6th, minus 64 over 6 factorial x to the 7th, and so on. I could spend a little bit of time and use maybe a floor function, but we might as well just write this then as 1 plus x times the cosine of 2x is equal to, well, I've got the same coefficient on x to the 0 and x to the 1st, and then x to the 2nd and x to the 3rd, so I'm just going to combine those things as the sum from n equals 0 to infinity of negative 4 to the 2n over 2n factorial times x to the 2n plus x to the 2n plus 1. And that's not in sort of formal power series form, but it's probably a more useful form than trying to figure out what floor function I have to use on my exponents and things to get this nicely. So there's an example, and if I wanted to evaluate that at some value, I could just plug it into this Taylor series. Let's see one other sort of thing that we can do with Taylor series, and let's try and find the Taylor series for example x plus 1 over x squared. Let's go with a minus 2x minus 3. How about a plus 2x minus 3? I think that'll work out better for me. Okay, so if I factor the denominator, I get x plus 1 over x minus 1 x plus 3. Right, and now we could use partial fraction decomposition. Well, let me mention first, if I was going to try and find the Taylor series for this rational function just by taking derivatives, I'd have to use the quotient rule, and I'd have to repeatedly use the quotient rule and then try and find a pattern from evaluating those quotient rules, and that would be a big mess. So we're going to go about this in a little bit more clever fashion to try and find a Taylor series for this rational function. And what we're going to do is we're going to factor it, and we're going to use partial fraction decomposition. So partial fraction decomposition, I've got two linear factors in the denominator. I'll be able to write this fraction as a over x minus 1 plus b over x plus 3. And so this is equal to a times x plus 3 plus b times x minus 1 all over x minus 1 times x plus 3. I want my numerator to equal x plus 1 no matter what x is, so I've got x plus 1 should equal ax plus 3a plus bx minus b. So we saw the method where I could just put in x equals negative 3 and get rid of all the a's, and that would tell me what b is, and I could put in 1 and see what would disappear, and or the b's would disappear, and I would see what a is. But let's just do this by setting the x values equal to each other. I get 1 times x equals ax plus bx, which is going to tell me that 1 has to equal a plus b. And I get that 1 is equal to 3a minus b. So I've got 1 equals 3a minus b. Alright, if I add these two together, I get 2 equals 4a, which tells me a equals 1/2. And then b has to equal 1/2 as well then. So there's my partial fraction decomposition. It was x plus 1 over x minus 1 x plus 3 is equal to half of 1 over x minus 1 plus 1 over x plus 3. Okay, so let's use this for our Taylor series expansion. Okay, so these look kind of like a geometric series expansion, so let's write them a little bit more like that. This is going to equal 1/2 of negative 1 over 1 minus x. Now that looks like a over 1 minus r for sure, where a is negative 1 and r is equal to x. Plus, and on this one I'm going to divide the top and bottom by 3. So I've got 1/3 over 1 plus x over 3, or because I want to look like a geometric series, I'm going to do a subtraction and a minus x over 3. Okay, now these look almost exactly like geometric series. They are actually exactly Taylor series. I'm going to have a negative 1/2 over 1 minus x plus a 1/6 over 1 minus negative x over 3. Okay, so let's put these together into a Taylor series. This is the sum of 1/2 times x to the n with a minus sign there from n equals 0 to infinity, plus this is the sum of 1/6 times negative x over 3 to the n from n equals 0 to infinity. I want to combine these, so I'm going to try and pull out everything except for the x to the n's in each of them. I've got the sum from n equals 0 to infinity here, minus 1/2 x to the n plus the sum from n equals 0 to infinity of 1/6 times negative 1/3 to the n times x to the n. So I could rewrite these by combining like terms as the sum from n equals 0 to infinity of negative 1/2 plus 1/6 times negative 1/3 to the n x to the n. And that is exactly equal to x plus 1 over what was it, x squared plus 2x minus 3. Okay, why would I want to do that? Well, like I said, taking the derivative of this rational function a lot of times would be really messy. We could figure out what the radius of convergence of this was, and within that radius of convergence we could easily show that the derivatives and everything are going to work fine. So what if I would ask, what is the derivative, let's say the 15th derivative of x plus 1 over x squared plus 2x minus 3 at x equals 0? Well, I'd want take the quotient rule and use it like 15 times, but that sounds like a very messy, long, arduous process. So we're just going to use this Taylor series that we just came up with, and I know that the 15th derivative, well, the 15th coefficient is equal to the 15th derivative at 0 divided by 15 factorial. So the 15th derivative at 0 is going to be 15 factorial times c sub n, which is 15 factorial times minus 1/2 plus 1/6 times negative 1 over 3 to the 15th, which would be a lot easier. Well, that whole process right there, after we did the Taylor series, or found the Taylor series, was a lot easier than taking the quotient rule 15 times. And I think probably finding the Taylor series took us as much time as it would have taken us to find the third, fourth, fifth, probably at most, derivative of this rational function. Okay, so there was just a few examples of what you can do with Taylor series. I think that's what we'll call it good for this week. We'll start seeing some more stuff, applications and things like that next week.